There we go. I've got block 2. They're recorded. Block 3. They're recorded, you guys. So in block 2, I answered these ones. In block 3, I answered those ones. I'll go over, and some of them are repeats, but it doesn't matter. I'm happy to go over anything you want. So what would your class like? Yes. So do you have a question where you were like, I don't know how to do this one, or I was confused by this one? 3.2F? Okay, do you want to find it? Whew. 3.2B, number 7. Yes, we can. Anything else? 3.2I, number 1 and 2. Excellent. There is a 3.2J. It's just like extra practice. Do you know what I mean? It has an answer key, but it does not have worked answers because there were 20 questions and I did not have it in me to type up the answers for that. It would have taken me hours and hours and hours. So 3.2D, number 4. Number 5. 3.2J, number 19. All right. If you think of more, you can always ask for more, but we'll start with this. We'll start at 3.2B, number 7. Uh, 3.2B, number 7. Okay, this is a challenge question, so you will not have a question like this with so many different components on your quiz, but it is a good review of both parts because we have a 40 ml sample of saturated barium hydroxide. I'm just rewriting down the question over here so that I can work it over there. Is neutralized by 29.10 milliliters of 0.300 molar HCl. Calculate Ksp. Now this one's a little weird because this is not what we normally see when it says calculate Ksp. However, if we want to actually calculate Ksp, would we be able to do that if we knew the solubility of barium hydroxide? Is that possible? Is that something we know how to do? Given a solubility, find the Ksp. Yes. Okay. So what is solubility again? That is the concentration of barium hydroxide saturated, yes? So what that tells me is now I can fill in some more information for my barium hydroxide. I have 40 mils, and I also have an unknown concentration. Yes, and that is for barium hydroxide. I have some other information about the HCl. I know that for HCl, we have 29.10 milliliters, and we know that it is 0.300 molar HCl. Is that a kind of problem that you can solve? Find the concentration of barium hydroxide, if you know its volume, and you know that it reacts with HCl of a known volume and a known concentration. What kind of a problem is that? It's a stoichiometry problem, yes? It's a titration / stoichiometry. And so we're going to do that part first in order to find the solubility. And then once we know the solubility, we can find the Ksp. So it's like a two-part problem. So we are going to start with the titration part. In order to do a titration question, what do you need first? You need a balanced equation. Yeah? So we have barium hydroxide, and it is reacting with HCl. And remember, this is always going to be a precipitation reaction, okay? Not precipitation, double replacement. That's what I'm trying to say. Because this is not a precipitation reaction. We end up with our outside ions give us barium chloride, BaCl2. And our inside ions give us HOH or H2O. In order to balance this, look at your ion concentrations, or sorry, not your ion concentrations, look at the ions in the salt, which is our barium chloride. We have 2 chlorides, so that means we need to put a 2 here. And if you have any trouble balancing the rest of it, just remember that hydrogen reacts with hydroxide like this, which means that the number of hydrogen is going to equal the number of hydroxide, which is going to equal the number of water, because these are all 1 to 1 to 1. That's our net ionic equation. Yeah? And 1 hydrogen requires 1 hydroxide to react with it. And in fact, if we look right now, I have 2 hydroxides and I have 2 hydrogens. So how many water would that produce? 2, right? If I had a 2 here and a 2 here, then I would end up with a 2 there. So I'm going to have 2 waters here. Okay, so now I have my reaction. The first step in any titration problem is to find moles of the known substance. This is what we call our known substance because we know the volume and we know the concentration. Barium hydroxide is our unknown because we don't know its molarity. So we're going to find moles of HCl. You want to do this all in one line? Okay, so we want to find the concentration of barium hydroxide. We're going to start with our volume. I would always recommend in a titration, when you're doing the conversions thing, start with the volume. Some people try starting with the concentration and then they get a little messed up because then they're like, oh, now I'm multiplying by liters, but there's nothing on the bottom of the liters, and that's okay. You can totally do that, but you need to let it not throw you. You know what I mean? Okay. So let's start with our liters, 0.02910 liters, and that's of my HCl. And I want to first find the moles of HCl. So we need to cancel liters. Do I know the moles per liter of HCl? Yes, it is given to us in the question, 0.300. 0.300 moles per liter. But I don't want moles of hydrochloric acid, I want moles of BaOH2. Because that's where I'm trying to get to, yes? BaOH2, and we need to cancel moles of HCl. And where do we get the numbers for that? Mole ratio. So there's 1 barium hydroxide for every 2 moles of HCl. Okay, sorry, it's doing weird things to me here. All right, and then finally, I want to find concentration. What is concentration measured in? Moles per liter. I have moles. How am I going to do per liter if I want it all in one line? I'm going to put 1 over the volume. Yeah, 1 over the volume, and the volume of the barium hydroxide is, going back up here, there it is, 40 milliliters. 0.0400 liters, and we get 0.0291 times 0.3 divided by 2 divided by 0.04. 0.1091 molar. So that's like part 1 of the question, is that titration part. Part 2 of the question is we're going to use the barium hydroxide, right? Because this is the concentration of barium hydroxide saturated. That is our solubility. And we're going to use that to find the Ksp. And pretty much all the questions that involve Ksp are going to do 3 things. They all have these in common. You're going to find your ion concentrations. I mean, I think there's one where you don't do that, but you know, most of the time you're going to find your ion concentrations. You're going to write your solubility equilibrium equation, and you're going to write your Ksp expression. And even if you don't know what to do with those, you've still got 1.5 marks just for finding those things, right? And if you're lucky, the ion concentrations might even be worth a whole mark. So look at that, okay? So let's find our ion concentrations. Concentration of barium. How are we going to find that? We know barium hydroxide. Is it the same? Is it different? They're equal because this is a 1-to-1 ratio, yes? So it's going to be same as the concentration of BaOH2. So that's going to be 0.1091. How about the concentration of hydroxide? Is it going to be the same? Half as much? Twice as much? Squared? 2 times concentration of barium hydroxide. If you prefer, like if this causes you discomfort and you're like, I don't know why that's 2 times, there are other ways of showing the work. You can say, okay, concentration of hydroxide is equal to 0.1091 molar barium hydroxide times 2 moles of hydroxide for every 1 mole of barium hydroxide. Yeah? And sometimes for some people that makes a difference so that they can actually see that. If you don't like that, there you can also show it, you know, underneath your solubility equilibrium expression or equation. If this is 0.1091, then this, which is 1 to 1 to 2, this is 0.1091, and this is 2 times, because of that 2 there, 0.1091. I don't care which way you show your work, whatever makes the most sense to you. Yeah? Pick one that you like. All right. Then we're going to have our solubility equilibrium equation, which I already wrote over there, but I'm going to write it again so it's all in line here. BaOH2 solid, Ba plus aqueous plus 2 OH minus aqueous. And then we have our Ksp expression. Ksp is barium concentration times hydroxide ion concentration squared. And that is 0.1091 molar. And the hydroxide is, oh, I did not multiply this. What a doofus. Okay, there we go. Sorry, times 2 equals 2.1825. There, that's better. 2.1825. No, oh my God, it's been a long day. I've done this question 3 times now, so I'm getting a little like, woo. Sorry about that. I will attempt to focus a little bit more. There we go. And now we're going to square it. All right, squared times 0.1091, and we get 5.1968 times 10 to the negative 3. We would need to go back and look at our sig figs, which I think is 3, if I recall correctly. Yeah, all our molarities and all our volumes are 3 sig figs, so this is going to have to be 3 sig figs. So that will become 5.20 times 10 to the minus 3. All right. Where am I going? I don't know. Did you guys need another minute with this, or are we? You're good? Okay. So we need to now find what I was going to answer next. So that one is done. Let's do 3.2D, number 4. 3.2D, number 4. Part of the tricky bit with this question is figuring out what it wants you to find. You want the grams needed to saturate a certain volume. So you want the grams per liters, yes? So you want to find the maximum grams per liter. What is the maximum grams per liter? Like, what word would we use for that? That is saturated. And if we're finding grams per liter of a saturated solution, we are finding the solubility. So this question is finding the solubility. And that's maybe the trickiest part of that question, is just figuring out what it wants. Yes? In any question where you are asked to find the solubility, so if we have a find the solubility question, what's the first thing that you do? Let X be the molar solubility of, what was our compound? MgOH2. Molar solubility, that's going to be our moles per liter. And do you see how if we can find moles per liter, we could also find grams per liter, which means that we could figure out how many grams are in 1.5 liters as well. Okay. Second thing we're going to do, write our solubility equilibrium equation. So this is for MgOH2 in equilibrium with Mg2 plus 2OH minus. And the third thing we're going to do is plug in the x's. So these are our concentrations. And the concentration of MgOH2 is its solubility, that is X. And Mg, we just get 1. And OH, we get 2. Can you guess what the fourth thing we're going to do is? It's one of the things that we always do. Ksp. Ksp is equal to Mg2 plus times OH minus squared. What do we do with those x's now? Plug them in. X times 2x all squared. That gives us x times 2 squared is 4, and then x squared. And then finally that is 4x cubed. And our Ksp, well, if we have an x, then Ksp has to be known, because we can't have two things that are unknown. That would make no sense. We're not given it in the question, so where do we go? Data booklet, there we are. Magnesium hydroxide, 5.6 times 10 to the minus 12. 5.6 times 10 to the minus 12. Solve for x cubed, that is 5.6 times 10 to the minus 12 divided by 4. X cubed is, let's see, 5.6 times 10 to the minus 12 divided by 4. 1.2, 1.44 times 10 to the negative 12. And then we take the cube root of everything. And we get 1.12 times 10 to the negative 4, but we use 2 sig figs, so that's going to just become 1. Oh, actually, no, I'm going to keep an extra digit. In fact, I'm going to keep a couple extra digits. 1.118 times 10 to the negative 4, because I'm not done this question yet, right? That is my X, that is my molarity of, who was the compound we were looking at? Magnesium sulfate or hydroxide. Now the question actually asked what mass of MgOH2 will saturate, what was the volume? Was it 150 mils? 1.5 liters. I was close, only up by a power of 10. Well, this is our saturated concentration, yes? So if we want to find the grams of MgOH2, why don't we start with this 1.5 liters? We need to convert liters into moles. And the reason we're going to moles is that we know the moles per liter, okay? So we know that there's 1.118 times 10 to the negative 4 moles per liter. And we want the mass, so we need to cancel moles and find the mass. Well, magnesium is 24.3, oxygen is 16 times 2, and hydrogen is plus 2. 58.3 grams of MgOH2 per mole. .118 times 10 to the negative 4 times 1.5 equals 9.776 times 10 to the minus 3, but we can only go to 2 sig figs, so that is going to become 9.8 times 10 to the negative 3 grams. All right, how are we doing? Okay, what other questions did we have? Let's see. So we've done that one, we've done that one. We want to do 3.2F, number 5. Number 5, okay, this is an excellent question. I love this one. So we have here, we have titrated 25 milliliters of HBr with NaOH. And because this is a titration, I'm going to write the titration equation. HBr plus NaOH gives, that's a 1-to-1 because there's just 1 and 1. So it's going to give me H2O plus NaBr. Which solution is the standard? Well, we have some information given here about the sodium hydroxide. We know the concentration and we know the volume of the sodium hydroxide. We only know the volume of the HCl. So who is the standard? The NaOH, because that is our known, yes? Which solution is the sample? Well, whichever one is the unknown is the sample, so that's going to be our HCl. Why should our average volume not include the starred volume? Let's take a closer look at those. Why am I leaving out this one? It's more than 0.2 milliliters different from the others. So it's an outlier. Calculate the average value of NaOH. So don't forget, this is like apparently, oh, I don't know, it was funny. When we did this, so many people asked me how to calculate an average, like so many. I think it's because you're in grade 12 and there's so much stuff in your brain that things that you learned in, I don't know, grade 5 or whatever have just fallen out because there's no more room, right? Anyway, just calculate an average like you would in grade 5. We've got 15.72 plus 15.79 plus 15.81. Those are all milliliters, and we're going to divide by 3. Oh, I didn't divide by 3. 15.77. There we go. 15.773 milliliters. There we go. That's better. Use this reaction to calculate the concentration of the HBr. Well, now we know that this is the volume of the NaOH. The concentration of the NaOH was up here, 0.500 molar. And we know that the volume of the HCl was 25 milliliters. We have our NaOH stuff here, and we have our hydrochloric acid there, and we don't know the concentration of the HCl. When doing a string of titration calculations, I would recommend always start with volume. So start with volume, so that's going to be of our known substance. So we want to find eventually the concentration of the HCl, which is moles per liter. And we have 0.015773 liters times 0.500 moles NaOH per liter. I've written this inconveniently. I'm gonna get rid of that. Put it up here somewhere. Now I have room. So now we have moles of NaOH. second step is always to convert to the moles of the other substance, and it's a 1 mole of HCl for every 1 mole of NaOH. And if we're doing this all in one line, remember we have moles of HCl on the top, and we just want to have liters on the bottom. So what do we put on the top here? Just a 1. And then on the bottom, we need the liters of that. So that's going to be 0.02500 liters. And we would get 0.015773 times 0.5 divided by 0.025 is 0.31546 to 3 sig figs, I think. Yes, 3 sig figs. 0.315 molar, and our compound is the HCl. Hopefully that's what the answer says. Yay! Except for that, oh, did I have a different sig fig there? No, I got it wrong in the answer key. My sig figs are wrong in the answer key. There we go. So, all right. Excellent. Let's do 3.2i, number 1 and 2. It is found that many grams, so I'm going to rewrite this over here, 1.892 times 10 to the negative 13 grams of cadmium sulfide, CDS, will dissolve in 350 milliliters of water. And we get a saturated solution. And it says, calculate the Ksp. If you have a single compound and you want to calculate the Ksp, you are going to do that via the solubility. And remember, solubility is the moles per liter. So we need to take our grams and turn them into moles, and we need to take our milliliters and turn them into liters. So the concentration of CDS saturated is 1.892 times 10 to the negative 13 grams per 0.350 liters. But I don't want grams, I want moles. Yeah. Cadmium, CD, 112.4, 112.4, plus sulfur, 32.1, 144.5 grams of CDS per 1 mole. My grams will cancel out, and I'll just be left with moles per liter. 1.892 E13 negative divided by 0.35 divided by 144.5 equals 3.74 times 10 to the negative 15 molar. What are the 3 things I should do in any question involving Ksp if I don't know what to do? Ion concentrations, solubility equilibrium equation, and Ksp. Well, oh, I love this one because this is 1 to 1 to 1, so I can just say this is equal to the concentration of cadmium, and it's also equal to the concentration of sulfide. Yes, so that's really nice. My solubility equilibrium, that's also going to be pretty easy. CD, S, solid in equilibrium with CD, 2 plus S, 2 minus, aqueous, aqueous, and we get Ksp is cadmium times sulfide is 3.74 times 10 to the minus 15, and I'm just going to square that because it's the same for both of them. And we get 1 point, how many sig figs? 3? Oh, 4 sig figs. 1.399 times 10 to the negative 29. Okay, just go stretch for a minute here, and then we will do the next one, number 2. Calculate the maximum mass of MgOH2, which will dissolve in 150 milliliters of water. Okay. So, maximum mass of MgOH2 that will dissolve in 150 milliliters of water. Well, I want the mass that will dissolve in a particular volume. What's that? Solubility. So the tricky part of this question is saying, what is the question asking me for? If I want the mass in the volume and I want the maximum in particular, that's going to be our solubility. So we're looking for solubility. And when we are finding the solubility, what is the first thing we do? Yeah, let X equal molar solubility. Moral solubility. Oh, that's awesome. Molar solubility of MgOH2. Second thing we do, one of the things we always do, solubility, equilibrium, equation. MgOH2, blah, 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 blah. Mg2 plus, 2OH minus. And then the third thing, because we're putting in X's, we're going to put in our X's here and here and here, except that I forgot the 2. There we go. Okay. Step 4, Ksp equals Mg2 plus times OH minus squared equals X times 2X squared, which is X, times 4X squared, which is 4X cubed. And then hopefully our Ksp is somewhere or other. Oh, magnesium hydroxide, 5.6 times 10 to the minus 12. X cubed is 5.6 times 10 to the minus 12 divided by 4. X cubed is 1.4 times 10 to the minus 12. Take the cube root of that whole thing, and you get X is equal to 1.12 times 10 to the minus 4. In fact, I'm going to write it as 1.118 because we are not done yet, because that is the concentration of MgOH2. But that's not what we were asked for. We were asked for the mass that will dissolve in 150 milliliters. So now we're doing some conversions, and when you're doing some conversions, start with the volume. So we want to find the mass of MgOH2. We're going to start with 150 milliliters. Oh, I should convert that to liters. 0.1500 liters times 1.118 times 10 to the negative 4 moles per liter. And now the mass, grams per mole, 24.3 plus 16 times 2 plus 2 is 58. Woo, 58.3 times 1.118 times 10 to the negative 4 times 0.15 is 9.8 times 10 to the negative 4. And if we look, did our units work out to grams? Yes, they did. I think we have one more question, and it was yours. Shall we do it? We have time. Let's do it. Jay. Oh, sorry. There. Yes. You can put the liters last. It doesn't matter where you put it. I like to start with the volume, but you can totally put the liters last. When you're multiplying, the order does not matter. You can put them in the middle too. You can do like moles per liter times grams per mole. Any of those work. Okay? J. Oh, I got to add a new page for this one and insert it. Okay, give me a second here. Add a page. Insert. File printout. Oh, okay. J. Insert. Oh, come along. You can do it. I know you can. Oh. Yay! Oh. Yay! Okay, number 19, right? Yeah. Okay. Oh. Ah, all right, okay. Number 19, calculate the bromide concentration to begin precipitation of lead bromide from 0.9 molar bromide, blah, blah, blah. Okay, so when you have to begin precipitation, these kind of questions, this is your min-max kind of question. And any of those kind of questions, you will be given 2 out of 3 things in Ksp, and you will solve for the third one. Okay, so we want to know the concentration of bromide. And we have lead nitrate, Pb, yes? On this one, you don't need to because you're not diluting anything. Yeah, if you were mixing, then you could. But this one just says calculate the bromide concentration, so you don't actually need to even do that extra step. Yeah? So for this one, we know that this is 0.90 molar. We don't know what this is. And we know the Ksp of lead bromide because we can look that up. And it says precipitation of lead bromide. So that is our precipitate. Lead bromide. Oh, is this the good one? Lead bromide, come on. Yes, it is. It's the satanic Ksp. Look at that. 6.66 times 10 to the negative 6. The Ksp of the beast. Sorry. 6.66. 6.6 times 10 to the negative 6. And that's our Ksp. Okay. So if we were to write our solubility equilibrium equation, because we always get marks for that, Pb, Br2 in equilibrium with Pb 2 plus 2 Br minus aqueous solid Ksp equals concentration of lead times the concentration of bromide squared. We know the concentration of lead because lead is 1-to-1 there, so that's going to be also equal to the concentration of lead. So we can just plug that in right down here. 0.90. We don't know the concentration of bromide. That's what we're going to solve for. So I'm just going to leave that as is. If you want to put an X in there, you can, but you can just leave it as concentration as well. I cannot have two unknowns. So if I don't know the concentration of bromide, I have to know the Ksp. So we can plug that in, 6.6 times 10 to the negative 6. And that means that bromide squared is equal to 6.6 times 10 to the minus 6 divided by 0.9, which is divided by 0.9, 7.33 times 10 to the negative 6, and that is bromide squared. So we need the square root of that whole thing. Bromide equals square root 2.7 times 10 to the negative 3 molar. That's all they wanted. So that's part A. Shall we see what's in part B? 19. Part B, what concentration, oh, this one's the tricky one. What concentration of lead remains after, and it's actually not tricky, it's just tricky because it looks tricky. Br has been raised to 3.0 times 10 to the minus 2 molar. Well, guess what? This time you know the concentration of bromide. You do not know the concentration of lead. But you do know that the Ksp is still 6.6 times 10 to the minus 6. So we're just going to do exactly the same thing, but in this case, our unknown is the Pb. Pb plus Br minus. So we're going to plug in, squared, sorry, Pb 2 plus times, this one is 3.2 times 10 to the negative 2. And Ksp is 6.6 times 10 to the negative 6. So lead then is 6.6 times 10 to the negative 6 divided by 3.2 times 10 to the minus 2. And, squared, 6.6 E6 negative divided by 3.2 E2 negative squared equals 6.44 times 10 to the negative 3 molar becomes 6.4 times 10 to the negative 3 molar. How are we doing? Did you guys survive that? This is all I've been doing all day long. I feel like I'm going crazy. Especially when I'm doing a question that I've done like 3 times. I'm like, such a sense of deja vu. Maybe I should have done it in accents. Different accent for every class. No, sorry. Yeah. Honestly, that's because the math part, not so bad, right? It's figuring out what you need. Very often, the question is asking you to find the solubility. If you're kind of like, I don't know, if it's asking you for grams, maybe it wants you to find the solubility. So just look for that kind of thing. Because yeah, it is, yeah, it's tricky. Tricky. I'm done. Anyone else done? Yeah. All right, I'm going to press stop recording.